Physics 2212, Lab 5, Magnetic Bracking with Faraday. The purpose of this lab was to utilize Faraday's law to analyze the interaction involved with a magnet falling through a tube of aluminum foil. We did this by collecting data through experimentation and then modeling the same situation computationally and then comparing the results. From this, we determined that in real life, the magnet fell at 1.20 seconds, but in the computational model, it took 0.915 seconds. So the main physics concepts used in this lab included Faraday's law, which was used to calculate the current induced in each ring by the falling magnet, the Biot-Savart law, which was used to calculate the force exerted on each current carrying ring by the falling magnet, Newton's third law, which is a law detailing equal and opposite forces, and it was used to determine the force exerted on the falling magnet by the whole tube of current carrying rings, and then lastly Newton's second law, which was used to write the position and velocity updating code to model the motion of the falling magnet. And these concepts were used primarily throughout the computational section. For the first part of the lab, we dropped a bar magnet down a tube of aluminum foil that was not ferrous and recorded the time it took for the magnet to fall through the tube. It was important that this tube that we used was not ferrous because if it had been, the magnet would have stuck to the sides. We did this procedure 5 times and recorded the time it took for the magnet to fall each time, and then we got the average of this time. From this part of the experiment, I got the average time to be 1.20 seconds. To go over what the code did a little bit, this code was used to simulate the situation that was used experimentally by modeling the bar magnet as a point dipole and the conductive tube as a stack of non-interacting conductive rings. From this, we were able to get the results as a visualization of the magnet moving through the tube, as well as a velocity versus time graph that updated based on the position of the magnet. To start off the code, the first thing I did was to input my physical constants, initialize the graph that was used for the velocity versus time, and then create the tube of aluminum foil using the measurements I gathered while doing the initial experiment. I then moved on to create the actual bar magnet using the mass of the magnet and the mu gathered from Lab 3, and then also start the initial conditions. Next, I used a function to calculate the magnetic field, which was also gathered from Lab 3, and then created a new function to calculate magnetic flux. Then I started the simulation loop, which was the motion prediction and then the visualization, as well as calculating the gravitational force on the magnet. I calculated the current in the ring and computed the typical B field at each ring. Lastly, I went on to calculate the net force on the magnet and then updated the magnet's velocity and position. Here are the results I generated, which included the velocity versus time graph as well as the visualization of the magnet moving through the tube. From this, you can see that the time in tube from the results yielded to be 0.915 seconds. Moving on to interpret the simulation, you could see from the previous slide that the red that was shown on the magnet as well as the blue that was shown on the magnet indicated the current, and the red was the clockwise and the blue was the counterclockwise, and this could be determined by using the right-hand rule. If you were to flip the orientation of the magnet, that would change the direction of the dipole, and then that would therefore change the current, but that would not change the speed. And so previously the flux increased downwards, but if you were to flip it, then the flux would then increase upwards. Also, comparing the experimental versus theoretical numbers, the computational system time in tube is lower, and this could be due to the calculated value of mu that was used in the code, which was gathered from Lab 3. It not being completely correct could have influenced that number, and had we added more rings to the model, we may have gotten a more accurate number. But the experimental could have also had some sources of error due to not correctly recording when the magnet entered and exited the tube. And then interpreting that shape versus velocity plot, you saw that initial deep plunge at the very start of the graph, which was from when the magnet first entered the tube, but then you saw that the graph leveled off once the forces on the tube started to balance and you got a net force of 0. So for the discussion questions, if the resistivity of the conductor were reduced as close to 0 to possible, then the magnet will fall a lot slower due to the increase in the induced current and the increase in magnetic force. And if there was holes or slits cut in the tube, then this would affect the ring by making the rings incomplete, which would reduce the induced current, making the magnet fall flat. In conclusion, by using our knowledge of Faraday's law, we were able to examine the interactions between the falling magnet and the inductive tube, and we saw that the magnet fell slower than it would have in free fall. From this, we were also able to get our experimental and our code simulated time and tube values, and we were able to understand that both the experimental values were affected by human error.